on a very important issue that is taking our days and our nights in discussing. And it is related to the leap second and the discontinuities in UTC. You know the story. To keep agreement with the rotation of the Earth, more or less every year we had one leap second. This was necessary in the 70s. Nowadays, navigation is not based on the traditional pointing to the stars and the planet. We have global satellite navigation system. So this addition of leap second, which is not predictable, not regular, is creating problem. Particularly remember that we have to add this second called 60. So we need clocks able to display the number 60 to be able to count this additional second. About 20 years ago, there was a first doubt on the fact that these leap seconds were still useful. And this was based on GPS. GPS system was born in the 80s. We said that GPS has a system times, which is called the GPS time. And at the beginning of the GPS history, GPS time was set in agreement with UTC. They started synchronized. But after that, UTC added 18 leap second, and GPS didn't. You may imagine when you have to manage an ensemble of satellites and you have to insert 1 second in a certain moment on all the satellites, and the receiver needs to be able to understand this change in the timekeeping, which is fundamental for the positioning. So this was considered too risky. So the GPS decided not to update any leap second on the satellite clock and on the reference GPS time. So in this moment, GPS time is ahead 18 seconds. And this happened also for the other navigation system. For example, GLONASS, the Russian system, applies leap second to have the GLONASS times in agreement with UTC. And we see GLONASS has always added leap second and sometimes was out of order for a few hours due to this fact. The Galileo system decided to use the same numbering of second of GPS, mostly for interoperability. So they are both 18 seconds ahead of UTC, while Beidou, which was born more recently, synchronized Beidou time with UTC, and now it is ahead of 4 seconds. So you see that we have a variable in the sky, and we can see on our smartphone the time coming from 4 constellations, and you can just choose as an option which is the time that you want to display on your screen. And if you choose GPS or Galileo or GLONASS or Beidou time or UTC, you have differences at the level of second. And these time scales are so easily available that as a user, if you are not educated, if you don't know all these differences, you can get really the wrong time by seconds if you don't pay attention. So a discussion was started 20 years ago, and it is now even more hot than at that epoch, because now we have digital networks, we have telecommunication network of clock inside financial center, network of clocks inside electric power distribution. And usually these clocks do not have the second 60. They are not able to cope with minutes, which is longer by 1 second. And this is mostly due to the fact that the computer inside this network is based on POSIX time, which counts the number of seconds since a certain origin, and each day is treated as a certain number of seconds, 86,400. So, for example, when one of the leap second was added, in POSIX time, this epoch was a certain number of seconds from this origin, and then again when second 00 came, the label was the same, Unix time, POSIX time is not able to make the difference between the second 60 and the following second 00. So we have 2 seconds with the same label, and so there is an ambiguity. And this is the main problem of the digital network. They are not able to correctly insert the second 60. And imagine, since we added the leap second at 00 in UTC on the Greenwich meridian, imagine in Asia, where it is 8 in the morning in China, 9 in the morning in Japan. It is the moment in which the stock markets open. We add the leap second, and this can be an enemy of most of this digital system. So different solutions have been applied. For example, the navigation system are not applying leap second after an initial synchronization, as we have seen. Other solutions stops the clocks and tick twice on second 59 or on second 00, as we have seen for POSIX time on many computers, but this is also for the NTP, the Network Time Protocol, and other type of time dissemination services. Or recently, Google has proposed to smear, instead of having a jump in time, what they do is they slow down the frequency of the clock, so it takes 1 day to accumulate 1 second delay and be again aligned with UTC. And for example, Facebook uses the same type of solution, but the second is smeared only on 18 hours, and the Chinese Alibaba is smearing 12 hours before and 12 hours after. So there is, during the leap second day, really a confusion in time scale, because this application is different in this different system. They disagree with each other, and particularly the users may not know which type of solution he is receiving from the network. So the fact is that UTC with the leap second seems not to be adequate to the modern application. Several solutions have been implemented, and we know that Google, for example, is proposing the smearing as international standard. For sure, they will try to have a single alternative solution. And these solutions are at the moment not compatible with UTC, and we think that if we do not modernize UTC, it will become less relevant and less useful. And particularly have a look to the estimation of the International Earth Rotation Services of the rotational time UT1 and UTC. Usually this difference goes towards 1 second. 1 leap second brings it in the positive. Then it becomes again negative, negative, negative. Usually when it reaches again about 1 second, a new leap second is added. But as I told you, in the last 5 years, we had the slowing down of the Earth was calming down. The Earth is not slowing down, even if it is accelerating. And if it goes down, up like that, we will not add a leap second, but we will remove 1 second to have UTC in agreement with the rotation of the Earth. And we think this will be really a problem, because that never happened, that has never been tested, and we would not like to witness the problem it can create. So the Consultative Committee for Time and Frequency is discussing this problem, and we would like to propose to increase the tolerance between the rotational time and UTC. We don't want to decouple. UTC will be in some way related to the Earth, but instead of being related within 1 second, which means adding a leap second quite often, we can just extend this tolerance to 100 seconds or even 1 hour. It will need a lot of time to be something important. So, for example, with the common rate of accumulating of delay by the Earth rotation, we will need 100 100 years to get 1 minute's delay, and we will need 5,000 years to get 1 hour of difference. So if we decide to fix the new tolerance to 100 seconds, we will be able to not to add anything for many years. We will not see this difference, because the rotation of the Earth has a seasonal variation which changes the duration of the day of 15 minutes, and we don't see that. It is a false perception, the fact that atomic time will tell you it's 8 in the evening, switch on the light when the sun is shining. This will happen in thousands and thousands of years. So what we propose is to extend this tolerance to measure very precisely which is the difference between the rotation of the Earth and UTC, but not to keep them in agreement so strictly within 1 second. The users of UT1, of the rotational time, have the possibility on the website of these international entities. They can find this value with microsecond uncertainty, so much better than the second tolerance that we have here. Navigation system, with some update, can disseminate this value. Maybe the old radio station will not be able to disseminate the code for this offset if it is larger than 1 second, but they can either modernize or stop this type of information. So this work is still in progress. Be aware of this issue. Try to be informed anytime there will be a discussion, either in the meteorological frame or in the ITU, the International Telecommunication Union, where this leap second practice was introduced. Try to be informed and to know which is the issue and why we are discussing that. And last of my topic is related to the possibility for timekeeping to return in space. So we said timekeeping and the second has been based on the observation of the Earth rotation since many centuries. Now we use atomic time, atomic clocks developed by physicists in the lab, not observing the sky. So by observing the sky, may we find some other clocks? Yes, there are rotating stars, which are called pulsars, which are built in such a way that they transmit a radio beam, which is like a lighthouse. They are neutron stars at the end of their evolution, which are very massive, and they have this radio beam which is spanning the space at any spin of the star, like a lighthouse. And particularly in the 80s, some pulsars called millisecond pulsars were observed, and they are very stable. This ticking is very stable. So there was a big of excitement. Is this a clock? Will timekeeping go again in space? Yes, it's nice to see. It's not so easy. First, imagine the star is very far, kilometer and kilometer of interstellar region, so there is a lot of noise. You have to integrate on many years to be able to see this stable signal. And then again, for friction, the star is rotating, so it is slowing down, and this deceleration has to be measured. There are no theoretical models accurate enough at the moment. We observe the pulsar from the Earth, which is moving in the space, so there are many corrections to be considered. But one of our colleagues, Professor Taylor, got the Nobel Prize for the observation of pulsar and the indirect proof of gravitational wave. And there are some work using pulsar to compare this celestial object with the International Atomic Time and see in the long term how the atomic time is behaving with respect to this very stable source in the long term. And particularly with the square kilometer array, which is under construction, a big network of antennas, of radio antenna that will be able to receive the signal from many pulsars, to discover many pulsars, it is possible that these small clocks in the universe will be able to form a precise ensemble time. And also, very interesting, a study which was carried out in the European Space Agency. Each star has its own rotational period and deceleration of the rotational period. So there is one star which is sending you a radio beam every millisecond, another one which is sending you a radio beam every 2 milliseconds or whatever. So imagine if you are in a space probe, a space ship in the universe, by observing the different stars and recognizing them by their different rotation rate, you can understand where you are, because you know that the certain star with a certain period is in certain direction, the other one is in another direction. So by the configuration of the sky that you are observing, you can estimate where you are. And so this comes back to what we say at the beginning. May we know the configuration of this special star so well to be able to understand and estimate our position by the observation of the different configuration of this object in the sky, so that nobody of medium intelligence will not be able to use them to identify the longitude and the position. And with that, I thank you very much for your kind attention. Thank you.